My name is Dr. Jere Drpic. I'm a senior assistant at the Institute of Archaeology. During my work, I use also mobile GIS application. I tested QField, but also merging maps. So for the QField app, first we need to prepare the project inside of the QGIS, and here I prepare some features that can be used later on in QField. Here I put some base map that can be used without internet connection, and also the layer called site. So first step is to open the application QField, and here we have a local project that we already prepared before in QGIS. Here we can just open it. We can upload the data that are prepared before, so vector layer with sites. Also we make a study area that we can turn on and turn off, and also the base maps that are very important when we are on the field to be independent from the internet. We have also the position. It is this blue dot. Here we have some features that are telling us how accurate it is and on what position we are, and if we want to digitalize some other features inside of the QField, we can do it easily with this plus button when we are on this location that we are satisfied. And here we have every element, for example name, also recorded date, period of the site. It can be easily selected with just one click. For example, if it's necropolis, and also some visibility that is very important in archaeology, if it's good, medium or poor when you are on the field. Also we have some other features like the description, interpretation, and some notes, and what is interesting here, we have also the photo that can be taken of the site and attached together with all other attributes of the site. So we can take a photo. Let's say this is a site. We take a photo, and here we go. We check this, and here you have a photo inside of the application. And if we are satisfied with all the data we just check this, and now we have other site that is over here. We can see a new site. Because of the GPS signal on the phone is not always accurate, as in forest environment and complex terrain, we can use handheld GPS, and because of this we can also have the accuracy of GPS device, and also the useful feature of the mapping that is provided by a QField app. With combining this, we can have a nice methodology for field collection.
Beneath the surface lies a hidden story, one shaped by time, geology, and human activity. Through advanced geophysical survey methods such as ground-penetrating radar, or GPR, and magnetometry, we are able to see what the eye cannot. These non-invasive technologies allow us to detect buried structures, map subsurface features, and identify anomalies without disturbing the ground. Fast, precise, and reliable. Geophysical surveys provide critical insights for archaeology, engineering, environmental studies, and construction planning. Ground-penetrating radar works by transmitting high-frequency electromagnetic waves into the ground. When these waves encounter different materials, such as soil layers, rocks, utilities, or buried structures, they reflect back to the surface, where they are recorded and analyzed. A typical GPR system consists of several key components: an antenna that both sends and receives the radar signals, a control unit that generates and processes the data, a power supply, and a data recording device or computer for visualization. Together, these components create detailed subsurface images, helping professionals make informed decisions without excavation. Ground-penetrating radar works by transmitting short pulses of high-frequency electromagnetic energy into the ground through an antenna. As these waves travel downward, they encounter changes in material, such as soil layers, stones, walls, or buried objects. When this happens, part of the signal is reflected back to the surface, where it is captured and recorded. In the field, the survey area is carefully divided into measured grids. These marked squares ensure systematic and accurate data collection. The GPR antenna is moved steadily along predefined lines within each grid, creating continuous subsurface profiles. At the same time, a total station or GNSS-RTK is used to precisely record the position and elevation of the survey grid. This guarantees spatial accuracy and allows the radar data to be correctly mapped and interpreted. The result is a detailed image of what lies beneath, without any excavation. Once data collection is complete, the recorded signals are processed and transformed into visual images of the subsurface. Each reflected wave is analyzed based on its travel time and amplitude, allowing specialists to identify changes in material and detect anomalies beneath the ground. The results appear as radar profiles and depth slices, revealing patterns that may indicate buried walls, foundations, voids, utilities, or natural features. By combining multiple survey lines across the grid, a comprehensive subsurface map is created. These images do not provide a direct photograph of what lies below, but rather a detailed interpretation based on signal behavior. With careful analysis, GPR results offer valuable insights that guide excavation, construction planning, archaeological research, and environmental assessments, all while minimizing disturbance to the site. We're very satisfied. The data quality is clear and consistent, and the grid system helped us maintain accuracy throughout the recording process. The combination of GPR and precise positioning from the total station gives us confidence in the interpretation. We're able to identify key subsurface features without excavation, which saves time and preserves the site. Overall, the survey met our expectations and provides a solid foundation for the next phase of the project. By providing accurate subsurface information in a fast and non-destructive way, GPR reduces risk, saves time, and lowers costs. Geophysical surveys using GPR and magnetometry give us the ability to see beneath the surface with precision and confidence. Through careful data collection, accurate positioning, and detailed analysis, we transform hidden signals into meaningful insights. Without excavation and without disruption, we gain the knowledge needed to plan, protect, and preserve. In the end, understanding what lies below is the first step toward building responsibly above.
Hello, I am Bisser Marinkov, an associate of the History Museum of Primorsko, and I will be introducing the topic of LiDARs, as well as sharing some of my personal experience and how this technology helps in archaeology, digital reconstruction, and preservation. LiDARs work by emitting rays of light that then bounce off of objects and return back to the emitter. By calculating the travel time of the rays and the GPS location of the LiDAR, it creates an accurate 3D model of the object or area.
Now, to explain the image you're seeing on screen. The raw data collected by LiDAR forms what is called a point cloud, which is comprised of millions of individual points in a three-dimensional space. These points are later processed into a detailed 3D model or terrain maps.
Here, we can generally split it into two categories: small portable LiDARs, such as the ones integrated into tablets, or bigger, more powerful ones attached to planes to map out an entire area of the land. First, let's begin by talking about the use cases, pros and cons of using small portable LiDARs. They are used for either small objects or small areas of the land, such as sectors of an archaeological site. Here are some examples of scanned objects. And now, for an example of an archaeological site. These scans help people working with 3D models, such as myself, to recreate objects and restore them. And now, let's take a look at more powerful LiDARs and their uses. They are mounted on aircraft or drone, fly over an area, scan the land, and make a 3D model, and showing interesting features of the landscape, such as straight lines and other features which might indicate human activity, and thus help archaeologists explore the land and make new discoveries.
An additional component used by such LiDARs is an IMU, which stands for Inertial Measurement Unit, and works as follows. It does not measure distance directly. Instead, it determines the exact position and orientation of the LiDAR during the scan. This allows the collected distance measurements to be placed accurately in 3D space. This is what the final result of an aerial scan would look like after it has been run through the proper software. The initial model is tidied up, removing elements like trees and vegetation, thus presenting a clearer image of the analyzed landscape.
With that being said, let's explore some problems of the technology. Since LiDARs emit rays of light, if we are to try to scan something that reflects light or lets it pass through, we run into some problems. For example, as you can see, this scan has multiple holes due to the fact that light passes through the glass. That's used for the restoration of the item, but the old Roman glass has enough impurities to allow the scan to work. Another problem we can encounter is specular reflection from shiny objects, and as such, we cannot get a proper texture of the item, or the 3D model might not even be made correctly. And lastly, dense foliage may cause issues and obscure important information. To sum up, LiDARs use three main components: light rays, which bounce off of objects and return to the emitter, the built-in GPS allowing it to calculate the distance and size of the objects, and lastly, photographic data, taken during the scan, is used to recreate the textures of the object. Having concluded my part, I thank you for your attention and send you my best regards.
This synopsis is a tutorial diagram that describes the 3D reconstruction using photogrammetric methods and digital imaging techniques of a sarcophagus unearthed during archaeological excavations in the eastern necropolis of ancient Chios from northwestern Turkey. The digital tools, their basic requirements, software and workflow to successfully complete the following steps and to obtain a basic 3D object as a result of the process are described in the manual. It should be noted that before starting, all necessary photogrammetry and 3D reconstruction software must be installed on the computer. This tutorial will use two free and open source software, Mushroom and Blender. Mushroom, a free 3D reconstruction software, offers 3D visualization capabilities using photogrammetric algorithms. Similarly, Blender, which is also free, is an advanced multi-interface 3D software capable of performing many operations such as modeling, animation, rendering, and 3D printing. Before we begin, it would be helpful to take a brief look at what a sarcophagus is.
In antiquity, sarcophagi were lead chests made of terracotta, wood, or stone used to bury the deceased or display them above ground. As archaeological cultural heritage, sarcophagi hold a significant place in human history, particularly becoming widespread during the Roman period, where they stored an important material for the burial of the deceased. Sarcophagi generally consist of two parts, a rectangular body and lid of the same form. Various figurative relief scenes, plant and geometric motifs, and architectural decorations may be found along the long and short sides, or they may be left plain and unadorned. Inscriptions relating to deceased and their family are often found on the long side of the body. The decorations, reliefs, and inscriptions, as well as the human remains, grave offerings, lamps, inventoriums, jewelry, clothing, and objects related to burial can be found within the sarcophagi. The finds constitute arguments that are meticulously examined for understanding, structuring, and dating past social life. Therefore, the documentation of sarcophagi and the finds discovered within them is extremely important as one of the fundamental application areas of archaeology.
So let's get started. Creating a 3D object from stereoscopic photographs requires photogrammetry software. Additionally, a suitable 3D illustration program is necessary to obtain 3D renders at the appropriate resolution. Users can choose between free photogrammetry software, such as Mushroom, or usually 30 days free trials of paid software, depending on their preference. Similarly, users should be aware that while there are free and open source versions of 3D illustration programs like Blender, there are also paid versions available for a limited time. For 3D imaging and reconstruction, the stereoscopic photographs of the objects should be taken, covering a 360-degree area. Stereoscopic photographs are images that create the impression of depth and solidity by juxtaposing consecutive photographs of the same object taken from different angles. Photographs of suitable quality can be obtained with a digital camera or a mobile phone. Generally, photos with a file size of 1 MB taken in suitable light conditions are sufficient. After the photographing is complete, the next step is to upload them to the photogrammetry software. Photos are dragged and dropped from their folders or imported into the software using the import command. The 3D modeling process then can be launched by pressing Start button in the software. The duration of this process varies depending on the quality and number of uploaded photos and the up-to-date status of your computer. It should take approximately 20 to 40 minutes to create a model from 30 to 35 photos, each with a file size about 1 MB. Photogrammetry software essentially prepares a 3D model after completing several steps, including aligning and matching photographs, creating depth maps, point clouds, and textures. The file is then ready to be exported using the Save As or Export commands. This allows us to keep our 3D model with the .obj extension to a suitable location on our computer, such as the desktop. Our 3D model, created using photogrammetry software, is ready. However, some vertex and texture irregularities can occur in the image. To correct and clean them, a 3D illustration program like Blender can be used. Blender is quite suitable for this process and has powerful interfaces. Now you can open the 3D illustration software and upload the 3D.obj file. In the window, you can see our 3D objects in various formats, such as solid, wireframe, material preview, and rendered. To edit and clean up vertex and texture irregularities, go to Edit Mode in Blender Wireframe interface. On the Z-axis, which defines the top view, select the irregular vertices and textures using the selection tool. Unwanted vertices will be highlighted in orange on the screen. Press X and delete them with the delete command. The process will be repeated until a clean 3D model is obtained. After a clean and suitable 3D model is ready, the next step is rendering process. You can render the scene as an image such as .jpeg file, or you can create a video by adding a camera to the screen.
Many historical objects carry inscriptions, marks, and textures that are no longer visible to the naked eye. Time, erosion, and material decay gradually erase these details. Even standard photography often fails to capture subtle surface variations. As a result, valuable information can remain hidden or seemingly lost. What is RTI? Reflectance Transformation Imaging, or RTI, is a computational photographic method used to reveal surface details. Instead of taking a single image, RTI captures multiple photographs of an object, each illuminated from a different direction. These images are then combined into a single interactive file. This allows the viewer to control the direction of flight digitally, enhancing fine textures, engravings, and inscriptions. RTI setup step by step. The process begins with preparing the object. It is placed on a stable, non-reflective surface alongside a scale reference and a reflective sphere. To achieve the best result, please use a black reflective sphere. A camera is mounted on a fixed position directly above the object. It is essential that the camera does not move during the capture process. The lighting is then introduced. A single light source is moved around the object, capturing multiple images from different angles. Each image records how light interacts with the surface. Typically between 20 and 50 photographs are taken to ensure accurate results. Consistency is key. Both the camera and the object must remain completely still throughout the process. Once the images are captured, they are processed using a specialized software such as Relight Lab. Relight Lab is an open-source tool designed for creating and visualizing RTI datasets. It enables users to transform a sequence of photographs into an interactive lighting model. First, the captured images are imported into the software. The reflective sphere is used to calculate the position of the light source in each image. The software then processes the dataset, generating an RTI file. This file encodes how light interacts with the object surface. Once processing is complete, the user can interact with the object digitally. By moving a virtual light source, previously invisible details can begin to appear. Surface features such as scratches, inscriptions, and tool marks become significantly more visible. This allows for closer analysis and more accurate documentation. RTI does not alter the object, but it can help to reveal it. By combining photography and computation, it allows us to recover details that would otherwise remain unseen, preserving not only the objects but the stories engraved within them.
Digital publication in the field of archaeology mainly refers to releasing one's academic or scientific research in an online issue. It can also refer to uploading a digital version of a print publication online. Both options are valid for archaeological data and digital products. Some examples of digital issues in Bulgaria are the Bulgarian e-Journal of Archaeology, as well as the contributions to Bulgarian archaeology. Examples from other countries could be the Internet Archaeological Issue of the University of York in the UK. Another one is the International Peer-Reviewed Journal of Archeologia Austriaca. Publishing material in such issues implies particular rules which are available online. Release in peer-reviewed digital journals could also be a challenging task. The availability of digital publication online is an invaluable instrument that aids the dissemination of research results in the field of archaeology and therefore supplements the wider popularization of historical and archaeological heritage. The online presence of academic publications makes them more transferable, easy to find, and it optimizes their citability. It also drives general academic research forward due to the easy and remote access to resources. Of course, when access to publications incurs a cost, limited number of people will be able to read them. In the technological age we are living in, the need for easily accessible specialized research has grown exponentially. In the last 10 to 15 years, there have been plenty of personal and organized initiatives to accommodate this need. Especially in the field of archaeology, I've been noticing many colleagues either publishing online in issues with open access or sharing their paper-based publication in a digital form free of charge. There are vast directories of open access academic literature which also cover the field of archaeology. Examples of open access platforms are academia.edu, researchgate.net, as well as the internetarchive.org. Of course, the risk of one's work being plagiarized rises due to the nature of digital documents. That, however, is mitigated by active copyright laws as well as open access licenses. Open access licenses, such as the Creative Commons licenses, can be used in conjunction with commercial licensing agreements. This way, researchers have a peace of mind that their work has some additional protection when shared with the public online. In conclusion, we will pay attention to the publication of archaeological data and the digital products generated from it. Online issues, such as the Internet Archaeology Journal, offers the option to publish such files officially. Publishing such data in a more casual way is also possible in platforms for 3D models such as Sketchfab, for example.